Greetings in St. LaSalle. Today I'm going to present to you our research entitled Quantum Capacitance and Surface Charge of Germanene, Silicene, Phosphorene, and Graphene using first principle calculations. It is an honor to be able to present this research at the DLSU Research Congress. Here's an outline for our presentation. First, we're going to quickly go through the introduction and then go into detail with the methodology, present the results, and then discuss the drawn conclusion in this research. Let us now begin. The future is renewable, and of course I'm talking about energy, and the sooner we make the switch from non-renewable resources to renewable resources, the better. But sustainability doesn't equate to efficiency, and we must find a way to efficiently store the energy that is harnessed from renewable resources. One way to do this is by using supercapacitors. The capacitor is made out of two metal conducting plates that is separated by a dielectric. The schematic of a supercapacitor is similar, however the electrodes are submerged in an electrolyte solution. This allows the supercapacitor to store charges like a battery and charge and discharge the stored charges like a capacitor. The capacitance of a material will determine its viability as an electrode. One of the materials used to manufacture electrodes is graphene. Graphene is a 2D semiconducting material with a zero bandgap energy arranged in hexes. Other examples of 2D materials are germanene, silicene, and phosphorene. This paper theorizes that these materials could compete with graphene in terms of capacitance. To prove this theory, we employed computational methods such as density functional theory, spline interpolation, and numerical discrete integration. And using these computational methods, we derived the key properties of density of states, quantum capacitance, and surface charge of the four materials named graphene, germanene, silicene, and phosphorene. Let's discuss the first computational method to be employed in this study. Density functional theory calculates the ground state of a multiparticle system by using quantum mechanics as a framework. It employs a handful of approximations to simplify the Hamiltonian for a multiparticle system. The Hohenberg-Kohn theorem states that the ground state energy is unique functional to the electron density, and the electron density that minimizes the energy of the overall functional is the true ground state energy. This means that solving for the electron density can be a prerequisite step for solving the ground state energy of the system. The Born-Oppenheimer approximation treats the atomic electron and atomic as an invariable because of the mass difference between the electron and the nucleus, while the Hartree approximation takes the average interaction of all electrons with each other and combine it in one term. An exchange correlation functional was then added to satisfy the Pauli principle, where an electron could not share the same quantum numbers as another electron. And the resulting eigenvalue equation that relies on the electron density is called the Kohn-Sham equation. This would yield the simplified wave function for the system. Now we can solve for another electron density. Here's the flowchart of density functional theory. First, we start with the original Hamiltonian, and then we simplify it using the approximations I said earlier. And then using the simplified Hamiltonian, we solve for the Kohn-Sham equation, which yields the size of R, which is the wave function. And using the wave function, we solve for the electron density. And using the new electron density, we insert it again to the potentials in the simplified Hamiltonian. We solve again for the Kohn-Sham equations, and using the simplified wave function, we can solve for another electron density. And we will do this again and again until we reach a point of convergence. The first parameter to be derived is the density of states. It's a mathematical function that gives the number of allowed quantum states as a function of energy that a particle can occupy in each material. It could predict the electronic properties of a material. It could also determine if the material is metallic, semiconducting, or insulating. The next property to be derived is the quantum capacitance. But how does it affect the total capacitance that I have mentioned earlier in the introduction? Well, it's one of the two components of the total capacitance. The electric double layer capacitance, or CEDL here, takes into account the interaction between the electrode and the electrolyte solution. And the quantum capacitance is derived from the electronic structure of the material itself. Below this formula, we can see the quantum capacitance, and it's reliant on the density of states, which we discussed earlier. It's followed by a thermal broadening function, which is a hyperbolic secant squared. Inside this function, we see E, which is the energy, subtracted by an external potential phi, divided by the Boltzmann constant and the temperature that we set to 20 degrees Celsius. This will be integrated with respect to E from negative infinity to positive infinity, but since this is reliant on the density of states, we're just going to integrate it all over the density of states function. Outside the integral, we see the elementary charge E followed by another Boltzmann constant in the denominator, and another 20 degrees Celsius. Below this formula, we can see the total surface charge Q. It's reliant on the quantum capacitance above. So we're just going to integrate it from 0 to a set potential value of phi, and then integrate it with respect to external potential phi. The external potentials will be set from negative 1 volts to 1 volts with 30 data points in between. Now let's discuss the methodology. First, we use density functional theory to solve for the discrete density of states. But since we are integrating, we need to convert it into a continuous function, so we use spline interpolation. And this new density of states function would then be substituted to the quantum capacitance equation that I have shown earlier, and using numerical integration, we integrated to solve for the quantum capacitance values. The quantum capacitance values was then graphed against the external potential phi, and this would yield another discrete function. We use spline interpolation to make this continuous. This will be the new quantum capacitance function that we will then substitute to the surface charge equation. And again, using the numerical integration, we solve for the surface charge values. And then we graph the surface charge values to the external potential values that we have set. Here's the model for all 4 materials that we have used. So we used a 1x1 supercell. So the supercell size is just 1 times the lattice constant A, and another lattice constant A here. The vertical vacuum size is 20 plus d angstroms, where d is the vertical distance between the 2 atoms shown on the left. Here are the parameters to our DFT calculations. The exchange correlation functional used in the study is the Purdue-Berg-Urzenhoff with van der Waals corrections. The K-point sampling was selected to be 33 by 33 by 1 with a cutoff energy of 550 electron volts. The quantum capacitance and surface charge graphs was then fitted to a polynomial function and an exponential function as needed. Now I'll present the results of this study. We can see here the density of states plot. You can see that the values of graphene is relatively lower than that of silicene, germanene, and phosphorene. For all 4 materials, we can see a lack of states in the Fermi level. It is also worth mentioning that the band gap of phosphorene is larger when compared to graphene, silicene, and germanene. Now let's take a look at the quantum capacitance values. We can see that germanene and silicene has high quantum capacitance values when compared to graphene and phosphorene. But it's also worth mentioning that phosphorene exhibited high growths in quantum capacitance values around negative 0.8 volt and 0.8 volts. Graphene has the most symmetrical quantum capacitance curve among the 4 materials discussed in this study. Now let's compare the quantum capacitance values of graphene and germanene for this study and to the others. For the graphene, we can see that the quantum capacitance value around negative 0.6 volts and 0.6 volts is 20 microfarads per centimeter squared, which is the same for this study from Zan, which is around 20 microfarads per centimeter squared as well. Looking at germanene, we can see that there's a discrepancy between the values of our study and Zhou's study. At around negative 0.6 volts, we can see that this is around 80 microfarads per centimeter squared for their study, but in our study, it's around 60. Around 0.6 volts, we have 80 microfarads per centimeter squared, while germanene has around 100. The deviations between the quantum capacitance values of this study and to the other studies could be an effect of the different parameters used for their DFT calculations. Now let's take a look at the surface charge values for all 4 materials. You can see that germanene and silicene has higher surface charge values than that of graphene and phosphorene. Well, this is to be expected since we saw that the quantum capacitance of germanene and silicene have higher values in general than phosphorene and graphene. Graphene is again the most symmetrical among the 4 materials, and phosphorene has the least surface charge values. Despite the differences in quantum capacitance values, particularly in germanene to this study and Zhou's study, the surface charge values of this study to Zhou's study for germanene remains relatively the same, and the same thing could be said for Zan's study for graphene. Now let's discuss the quantum capacitance fitting for all 4 materials. Graphene, germanene, and silicene was fitted to a parabolic function, and phosphorene was fitted to a exponential function. The A value of graphene is lower than silicene and germanene, This means that its quantum capacitance grows more slowly as the potential increases. Graphene has the closest A value, meaning that it has the most symmetrical quantum capacitance curve when compared to silicene and germanene. The A value of silicene in the negative side indicates that it has the fastest growth of quantum capacitance values as the potential increases below 0 volts. Germanene exhibits the same property but for the positive side, since it has the highest A value on the positive side. Taking a look at the A, B, C, D values for phosphorene, C and D indicates the position of where the exponential growth happens, and the low values of C and A for phosphorene indicates that it happens further from the origin, which is at 0 volts. We can see that the D and B values are high, so this means that phosphorene exhibited rapid quantum capacitance growth but away from the 0 volt potential. Now let's discuss the exponential fitting for the surface charge. For positive potentials, judging from the growth parameter alone, we may see that phosphorene has the highest surface charge value, but its A value would beg to differ. Phosphorene's smallest A value makes it so that the high growth rate will only happen when a high potential value is applied. From the graph, this is apparent as we see the value increase at 1 volt. Now, looking at graphene, yes, it has a high B and D value, but it has a low C value and A value as well. Now this leaves us with germanene and silicene. Out of the two materials, it's pretty clear that germanene has the upper hand due to its higher growth parameter and a higher A value, meaning that it happens at point close to the 0 volt potential. Looking at the negative potentials, the same can be said. Graphene and phosphorene's A value is too small that its decay behavior happens at very high potentials. For low negative potentials, we can see that silicene trumps germanene, but a look at its A value would say the opposite. Its significantly low A value renders silicene surface charge values lower than germanene, so for positive and negative low potentials, germanene takes the crown as the best material for supercapacitors in terms of surface charge and quantum capacitance. Now let's discuss the conclusions drawn in this research. For the quantum capacitance trends, we can see that germanene has the highest quantum capacitance. Phosphorene might take over silicene and germanene at high potentials, but this is assuming that the exponential increase continues beyond negative 1 volts and 1 volts. Now for the surface charge, germanene and silicene are recommended materials as electrodes since they outperformed phosphorene and graphene. Phosphorene has the worst performance, even though that it showed exponential growth on its quantum capacitance. It's not enough to surpass even that of graphene's surface charge. Graphene and silicene symmetry in quantum capacitance could be useful for AC applications. We would like to recommend to explore formation energies for structural stability and the effects of different supercell sizes on the key properties measured in this study. We would also recommend adding impurities in the material via doping or introducing vacancies, and again, see if there are any differences in the measured properties in this study. We would like to thank the Computational Materials Design Research Group in De La Salle University for supporting this study towards its completion, especially Dr. Melanie David and Dr. Alfred Villagracia. Here's the list of our references used in this presentation. That's all from us. Thank you and God bless.